Hi, everyone. Welcome to another ACE session. Thank you for joining us today. Just a little bit about ACE. We are a group that hosts online machine learning talks with leading researchers. We have multiple sessions each week, and all of the videos are stored online on our website. If you visit ai.science, there will be the videos as well as the paper links, sometimes the GitHub code and everything. So you can find that link in the description. So thank you very much. And today we have Professor Pascal Poupart. I'll give a quick introduction before I pass the floor on to him. I'm very glad to have Pascal today here with us. He is a professor in the School of Computer Science at the University of Waterloo. His research focuses on machine learning and decision theoretic planning with application to multiple fields. He's also the Canada CFAR AI Chair at the Vector Institute. He is the most well known for his contributions to algorithms for decision processes and their applications in real-world problems. So without further ado, let me pass the floor on to Professor Pascal Poupart.
Hey, thank you, Susan. So it's an honor for me to have the opportunity to present this work. So I guess the title for today is Object-Level Self-Supervised Learning to Speed Up Reinforcement Learning in Visual Environments. Okay, so what does that mean exactly? So we're going to be looking at reinforcement learning, and more specifically, there is one big bottleneck that many algorithms suffer from, which is data inefficiency. So I'm going to discuss one solution that is based on self-supervised learning. And in particular, the algorithm that I'm going to describe is known as MOREL, which stands for Motion-Oriented Reinforcement Learning. So it's going to be an algorithm that essentially exploits motion in video environments. We're going to do that again by self-supervised learning. And the benefit is that we're going to speed up the optimization of a policy, and also we're going to achieve some form of interpretability. So if anyone's interested after this to read more about this work, so this work got published in 2018 at NeurIPS, and the title is Unsupervised Video Object Segmentation for Deep Reinforcement Learning. Okay, so let's get into the meat of the problem. So we're looking at reinforcement learning. Here's a slide that summarizes in one picture what is reinforcement learning. So we've got an agent. It selects some actions. Those actions affect the environment, and then the agent would receive rewards and observations. And then based on that, it'll choose new actions. And the goal is to, in this feedback loop, maximize rewards, right? So there's lots of applications that can be formulated with this type of abstraction. And I've got a list below here. Okay, so now reinforcement learning works in those applications, but very often is not efficient. And as a result, many of the RL successes today are based on simulated environments. So we've had Atari, there's a simulated robotics like Mujoko, there's some video games like Vizdoom, other games like Computer Go, but what they all have in common is that these are simulated environments, so it doesn't matter how much data is needed because there's a simulator that provides it. And just to be concrete, so if we look at Atari games, so back in 2017, there was a paper by Schulman et al. That essentially studied some baselines. And then I'm plotting here the results for some of those baselines. And the key is not so much what the baselines achieve, but if we just look at the x-axis, okay, of all those plots, we see that these plots show results for up to 40 million frames. So what this means is that it requires a lot of interaction with the environment. Again, it's all done in simulation, so it's not a big deal, but for real-world applications, that can be a major bottleneck. And here, 40 million frames is a lot more game time than what a human would need to achieve similar results. So the question then is, how can we reduce that? So let's look at how reinforcement learning would be used now to optimize a policy, let's say to play in a video game, or otherwise, generally speaking, with visual environments. So we would first start with an image that is fed, and in fact, when I say an image here, it might be a sequence of images, but generally speaking, these are images. They're fed to a deep neural network, And this deep neural network is going to compute either some action or some values, and it would correspond either to a queue network or some policy network, right? And then based on this, the environment is going to return some reward. And very often, in many environments, the rewards are going to be sparse in the sense that only once in a while you get a reward signal. And beyond just being sparse, that reward signal consists of one number. So here I'm representing by a dot the fact that it's one number. And then if we have a neural network that has millions of parameters, and then at every time step we get 0 or 1 number, so you can imagine that it will take millions of frames or millions of time steps in order to train these millions of parameters. So this is no surprise, but then the question is, what can we do to perhaps speed that up? So self-supervised learning is something that became popular in computer vision. Back in 2018, there were several, I guess 2018, 2017, there were also several proposals in reinforcement learning where the idea is that you take advantage of the fact that in your data, you could construct some auxiliary task where the target is already available. So in that sense, it's supervised, but then you don't need to get anybody to label the data, so it's self-supervised. And those tasks are not the original tasks. So normally in reinforcement learning, we want to maximize rewards, but here we're going to instead try to make some prediction that will allow us to learn something about the environment. It's not necessarily in terms of maximizing rewards, but the information that's going to be learned will be useful for maximizing rewards down the road. So concretely, one of the ideas that you have your input image, then you can have a deep neural network that instead of computing an action or some Q value, will simply predict the next image. And that's useful because if you're planning while you're playing in a video game, then intuitively, you should be able to predict what is going to happen as a result of choosing some action. In other words, what are going to be the next frames. And if you can't do that, then obviously you don't have a good policy. So you should be able to do that in order to get a good policy. Now, the benefit of predicting the next image is that an image is itself millions of pixel intensities. So that's millions of numbers. It's a dense signal. And now you have a lot more information to train your deep neural network that has millions of parameters. So we'll see that we can do this a lot faster as a result. Okay, so beyond self-supervised learning, there's also some other aspects that make reinforcement learning slow compared to what humans do. And an interesting question is what prior knowledge do humans use that perhaps the computer may not have access immediately? So like, here are 3 Atari games, and if you've never played those games, that's fine. In fact, the beauty is that if you've never played those games, I bet that you can recognize immediately what are the objects in those games, what are you controlling, and what are the enemies, and what you might need to do, right? So you see this immediately. But then in contrast, when a reinforcement learning agent looks at those games, it receives a vector of pixel intensities, and that doesn't mean anything immediately, right? Like, it has to be interpreted, so features have to be extracted. So I guess to summarize, you see humans, they see moving objects, and we can start planning a policy immediately based on that, whereas a reinforcement learning agent sees a sequence of pixels and it has to first figure out how to interpret this. So this is a big difference that will also require a lot more data. Okay, so to I guess hammer my point here, so how exactly is the reinforcement learning agent going to interpret those pixels? So this deep neural network that we saw earlier, intuitively, we can think of it as having some layers at the bottom that are responsible for feature extraction, and then layers at the top that are responsible for policy optimization. I mean, here those layers are not designated specifically for those purposes, but intuitively, this is what tends to happen. And then so here you see the deep neural network has a lot of its layers really just focus on feature extraction, which for humans, we don't have to worry about that. Like we interpret, or we can recognize and understand those images immediately. So then the question is, can we further speed up reinforcement learning by trying to simplify this feature extraction part? In particular, since we know that these are games and often it's the moving objects that matter, could we get the agent to automatically learn to segment the moving objects? And then it could essentially play at a high level that would be on par with what humans would do. Okay, so now let me propose an algorithm that will achieve this. So the name of the algorithm is MOREL, which stands for Motion-Oriented Reinforcement Learning. And it consists of two phases. So in phase one, we're going to do object segmentation, but we're going to do this in an unsupervised fashion. And then I'll show you that we can achieve that by using roughly 1% of the frames at the beginning when the agent starts playing to learn how to do this segmentation in an unsupervised fashion. And here, because it's the beginning, it's okay for the agent to just execute random actions. So the policy won't be good, but it's just 1% of the frames, and it won't have much of an effect. Then in phase two, we'll have a way to segment objects that are moving, and then we'll essentially feed this higher level information to a policy network, otherwise a Q network, that will speed up the optimization of policy. So the reinforcement learning agent will be able to focus on a planning much more quickly as a result of that. So that will be phase two of the algorithm. Okay, so now let me explain how we're going to do the object segmentation. So here, it would be tempting to consider some supervised techniques. In computer vision, in fact, that can be quite labor intensive if we take an image and we want to label every single pixel as, let's say, being a car, being the street, being a house, a tree, and so on. Turns out that there's been a lot of work over past decades where you can leverage what is known as optical flow to essentially do some structure from motion. So if we have a video sequence and then there's a cyclist moving, there's some pedestrians walking, so they're moving, and then we can compute or we can estimate the optical flow of their pixels. And then because the flow will be similar for those pixels, that kind of gives you a hint that they must belong to the same object, and that already gives you good information to obtain a segmentation. So this is an idea that has been used quite a lot in the past in computer vision, and we're going to see how to combine it with reinforcement learning to obtain higher level information in terms of object segmentation and motion. Okay, so for this, what we did in our work is we took a neural network known as structure from motion network. This was proposed by Google in 2017. And this network was proposed for 3D environments. We simplified it to a 2D environment in order to apply it to Atari games. So our simplified network has the following architecture. So we feed in a sequence of two consecutive images. Then we have convolutional layers. They compute essentially an embedding of those images. And then from that, we're going to compute the object and camera translation. So this is their motion. And we're also going to compute object masks. So the masks are going to correspond to the segmentation. Now, when we combine the mask with the translation, we can compute the optical flow. So that's the displacement of every pixel from one image to another. And if we add the optical flow to the first image, then we can get a prediction for the second image, compare that to the ground truth second image, and then backpropagate through the network to essentially adjust all the parameters in order to learn to make predictions in this fashion. So the beauty of this network is that you just take a sequence of two images, and then you're able to train it without any form of labeling to implicitly infer object mask as well as translations. So that's the motion. And then this is done simply by verifying that you can predict what the next frame is going to be. Okay, so when we did this work, we essentially started from a structure from motion network that was proposed in 2017 by Google, but we made some modifications. The first one is that you'll notice in this network that there are no skip connection. So we'll see in a moment that it's important that all the information flows through, and that here we, in this layer in particular, that we have all the information going forward. Also, in terms of reconstructing the second image, instead of measuring the error using, let's say, Euclidean norm or some other common norm, we use a norm that is more suitable for computer vision, known as structural dissimilarity, and that focuses more on the structural aspects of the image. We also use a flow regularization, so L1 loss, and this helps in terms of making sure that the object masks are as small as possible, and also that the translations are relatively small. We also did curriculum learning. So when we optimize our network, we have a loss function to reconstruct, but also regularize, and then we gradually added the regularizer by increasing lambda from 0 to 1. So these are simple things that we did that were in fact critical to make this work in Atari games. So now, just to illustrate, this network, as I explained, it takes two consecutive frames. So here we've got an example with breakout. There's Pong. Breakout has a paddle and a ball. And the idea is that the paddle and the ball are going to move. So that's what gets recognized here. So we see the masks summed. So that means these are the masks of all the objects. So it roughly recognizes where the ball is and where the paddle is. Here we see the most salient mask, so that's the most important object, so that's the paddle, so it's a bigger object. And finally, we've got the optical flow. So here the color, so green and red, indicates the direction in which those pixels are moving from the first image to the second one. So that illustrates what the network does. We've got an example for breakout, also Pong, and if you go to our website, we actually have that for all 59 games from Atari. Okay, so then we applied this network to essentially learn to segment and therefore get masks and also motion. And now we feed that information to an actor critique that does reinforcement learning. So the network that we're looking at here is a combination of the top part, which does the object segmentation. Okay, so we've got here, so this is just a summary of the previous network that I showed before, where this layer corresponds to the layer after all the convolutions, and that's the bottleneck layer before we start computing the masks and translation. So this layer, in fact, contains information about the masks and the translation. So then we feed that to an actor critique network. So the bottom part is just a regular actor critique network. Normally, we would just have convolutions that process the image, and then after that, this would get fed to an actor network and a critique network. But now we concatenate the high-level information about the object masks and the translations with the low-level information that directly comes from these convolutions here. So the benefit is that now we'll have both high-level and low-level information in order to obtain, I guess, a good policy faster. So when we combine, so like this bottom network, think of it as being A2C or PPO or your favorite RL algorithm. Okay, and when we combine that with the top part that does the object segmentation, then we obtain better results. So that means we were faster in terms of finding a good policy for 26 games. It was roughly the same speed for 30 games, and it was worse in 3 games. For PPO, it was faster for 25 games, roughly the same speed for 25 games, and worse in 9 games. So let me show you now with some videos, 4 examples. And again, we've got videos for all 59 games if you want, but I'm just showing you 4 of them. So you can see on the left side is the classic view. On the right side is what our segmentation networks computes in real time. So it shows what objects it detects and what motion it recognizes. Okay, so you can see on the first 3 games, so Pong, Breakout, Sequest, it does very well, right? So it's capturing the objects quite well. When we look at Beam Rider, there's something interesting going on here because it is capturing the objects that are moving, but you'll notice that in this game, you see those horizontal lines that are just moving down the screen are just visual artifacts. They don't matter at all in the games. And now on the right side, you see we're capturing these lines coming down, but because they're not important for the game, so we're essentially capturing irrelevant information, and that will not help our reinforcement learning agent. So let's have a look at some performance curves. So here we can see in yellow our algorithm, MOREL, and then we've got several other baselines. We would like to achieve high reward as quickly as possible. And so that means that we want to have a curve that is as much as possible to the left and as high as possible. And the x-axis here is the number of frames, so that goes up to 10 million. So you can see that we can arrive at a good policy faster for Pong, for Breakout, and Sequest. For Beam Rider, you see we don't achieve a better performance, or we don't achieve we don't find a good policy faster simply because we're feeding in high-level information that is irrelevant. Yeah, so that explains why I guess it doesn't always perform better, and in some cases it might actually perform slightly worse, but that gives you a sense. We also did an ablation study to see among the different modifications to the structure from motion network from Google, the original one, what were those modifications that were really important. So for instance, you see we had some curriculum learning, we had an L1 loss, and also some regularization. And then if we remove those, you see that the performance goes down. So our algorithm is in blue. When we remove some of those modifications, the performance goes down, and that shows again that these changes were having an important impact. Okay, so this concludes what I wanted to present today. So I told you about an algorithm, MOREL, which is motion-oriented reinforcement learning. The beauty is that it can segment, therefore recognize both the location and the motion of objects in a completely unsupervised fashion. So nobody has to label anything. And then we don't have to provide any additional information than usual, just I guess the video sequence, and then it will extract this information. So this higher level information then helps with policy optimization. So we saw that we can reduce the time to find a good policy. It also helps with interpretability because then we can see what what is the information that is being fed to the network. So if the segmentation is wrong, or if it focuses on objects that are irrelevant, like in Beam Rider, that can help us understand why the policy it might not be better or worse than otherwise. Okay. Now, in terms of ongoing work and future work, so I do have some students who are currently extending this to 3D environments. We're also looking at object-oriented reinforcement learning. So you see the beauty is that we're extracting objects. There's a whole literature on object-oriented reinforcement learning that goes back more than 10 years, but historically this literature was assuming that somehow objects would become available, but nobody really had a way to extract the objects, or there would have to be some additional process that does that. Whereas now we have an unsupervised way of doing this, so effectively with our approach, we can enable all of that work on object-oriented reinforcement learning. And when you start reasoning at the level of objects, then we should be able to learn some models, so some transition models that would be more effective, and then we should be able to see some further reduction. So I guess this is ongoing work. Now, in a different direction, so with respect to text instead of images, we've also done something similar where we can automatically infer information about objects. These are entities and relations that are mentioned in a text. And we just published a paper at NeurIPS. The title is Learning Dynamic Belief Graphs to Generalize on Text-Based Games. And the idea is that, yeah, we extract objects and implicitly extract information about the knowledge graph that the text is really talking about, so that you can perform better in text-based games. So it's similar ideas, but with respect to text instead of computer vision. In any case, again, if you're interested to read more about this work, so it was published in 2018, and this was the title of the paper. So let me stop here, and I'll be happy to answer some questions.
All right, thank you so much. Yeah, and congrats on the kind of the other text-based games work being accepted to the NeurIPS 2020. So we do have some questions. So there was one slide that you had a like a phase 1 and phase 2. They're wondering if you could slightly elaborate on that.
Okay, so yeah, so phase 1. So I guess at the beginning, what happens is that in phase 1, we let's see. Okay, so when we're training this network in phase 1, we're essentially just training the top part of the network, and we don't bother training anything about the bottom part. So okay, like in the plots, the x-axis was for 1 million, 10 million frames, and then so we took 1% of those frames, which is 100,000 frames. So the first 100,000 frames were essentially just training the top part of the network. And then the bottom part, things were just initialized at random, and actions were just executed at random, but nothing was being optimized. Then in the second phase, now we start training the bottom part as well. And here we also keep training the top part, but what's important is that now we start optimizing the policy network and the Q network. So that's essentially what the two phases refer to.
Gotcha. Thanks. I think that's pretty helpful. So another question was, you mentioned I guess like the curriculum part of it, which changes the strength of the regularization. And then the paper says you have linearly increased it from 0 to 1. I guess is that a common approach, or are there other ways of let's say increasing it like even dynamically, or is it just like a common approach linearly?
Okay, so the linear increase, I mean, okay, so the people who really did this work were two students, Vic Goel and Jamison Wang, and they played with lots of ways of adjusting various things in the architecture and the training, and they found that curriculum learning works. They tried, I guess, increasing linearly, but I do not know if they tried other schedules. The point is that here you want to have something that gradually introduces the regularizer, but initially starts by just optimizing the reconstruction loss, because I guess you want to get a network that can first manage to reconstruct the second image by coming up with whatever object mask and translation vectors. But then after that, you see, you might obtain some object masks that capture parts of several objects, so that really, like, you wouldn't have one mask for one object, or you might have sometimes a mask that contains more than an object, but contains part of the background that is uniform, and then it looks like, oh, we could also do some translation that uniform background because there's no texture. So the idea is that once you can reconstruct the second image, then after that you want to make those object masks as tight as possible, so that they have better quality in terms of really corresponding to objects. And that's where the regularizer becomes important. But you don't want to start by regularizing immediately, because then it's too difficult for the optimization to really do both simultaneously, right? So that's why it helps to just start with reconstruction, and then after that kind of like fine tune those object masks and also the translation vectors by also applying the regularizer.
Gotcha. Thanks. That's really helpful. I guess just to add on that, would you say that so like throughout the training, then it's just easier to be able to focus on the reconstruction first, and then gradually kind of like dial that, if there's a knob, like you dial it to the other end rather than the other way around, right? Like it'd be harder to learn the reconstruction like after, if they would
Yeah.
have.
Yes. Well, yeah, because if we were doing it the other way around, starting with just a regularizer, then you see if we only optimize for the regularizer, we would say, oh, there's no object mask, right? So the size of that is 0, and there's no translation. So the size of that is 0 too. and then yeah, that wouldn't serve any purpose, and then we would try to do reconstruction after that. So that you can't go the other way around, really. So you really have to start with reconstruction, but then you don't want to impose too many constraints, right? It's like saying, okay, we're playing a game, but then in this game, we're going to relax the rules so that you can develop your strategy gradually, and once you're good at it, then we're going to start imposing the rules which will force you to really like play this game well. So I guess that's the idea here.
Gotcha. Yeah, that's really helpful to like clarify that point. There was another question, which is about the object mask and the optical flow. I think it was like a slide where you had images of both of them, or just like any of the slides will do. Like the one with the simplified yeah, this one. Yeah. So
This one, okay.
is the main difference between the yeah, because it seems like the masks are showing the learned relevant information at a snapshot in time, but the optical flow is more focused on like almost like a delta of time because it's like movement, right? Is that the case?
Yes, that's right. So yeah, so the masks are with respect to one image. So here, I don't remember if we go from image 1 to image 2, image 2 back to image 1. So I'm just going to assume that it was image 1 to image 2. So the object mask would correspond to essentially a segmentation of the objects in image 1. So it's just based on a snapshot. And then the optical flow is the delta that allows us to go from image 1 to image 2.
I see. So, actually, just out of just to clarify, like, does the kind of the optical flow end up as the only information that goes into the agent, or is it that both of them go into the agent and the train?
Okay, yeah, so that's a good question. So in terms of the information that goes into the agent, it's essentially, you see the information in this layer. So okay, the top part is again our segmentation network that first has some convolutional layers, right? And here, this part is where we compute object mask translation that culminates into the optical flow, right? But we do not feed the optical flow directly. We do not feed the object mask or the translation vectors directly. So what we feed instead is a layer that was essentially a bottleneck layer that necessarily contains all the information that is computed afterwards. So that means it has, from an information theoretical perspective, the information of the object mask as well as the translation vectors, and that's what gets concatenated here. So here, when the student did this work, they actually started by feeding in the object mask and the translation vectors, and the results were not very good. And then when instead they fed this dense layer directly, so they obtained better results. And here, this is a common phenomenon where very often, if you have structured information, like object mask would be essentially, you see a matrices of zeros and ones, or if it's with some uncertainty, probabilities between 0 and 1. So it's something very structured. and essentially there's no redundancy between the different entries in the object mask. Whereas here, when we have a vector that is a summary or that captures these object masks, then you see every label for every pixel is not represented explicitly, but it's sort of like, represented implicitly across the entire vector. And then there might be redundancy as well as part of this vector. So generally speaking, practitioners have found that it works better whenever you feed some vector that is, I guess, just a vector representation and embedding of the structured information. But then it contains the same information, it's just not structured anymore, because that gives more flexibility after that, and then it just tends to work better in terms of the optimization.
Okay, yeah, that makes sense to me. So like the kind of reason why you have that separate part with the optical flow is just because if it can accurately do that and you find out the kind of the embedding of the actual crucial information that is needed to do that, like you kind of are able to compress it and then feed it into the actual kind of training portion. Like you're almost using it as a way to find like good like good embeddings or features to actually help and then speed up the process.
Exactly. Right? Yeah.
Awesome. So is that the main reason why? Because I guess you mentioned that this speeds up the process. Like, is this the core reason why, or is this one of the reasons?
Yeah. So
speed.
Yeah, that is the core reason why. So if we go to the results here, okay, so you see our algorithm, which is A2C plus MOREL, is in yellow here. And then we have as a baseline just A2C. So the green line here would be essentially just the bottom part, okay? So the green line was if we just had an actor critique by itself. And then the yellow line is when we have the full architecture that includes the segmentation network. So then the segmentation network, you see with this edge here, provides information about the objects. So it essentially does the feature extraction for the network. And then the actor critique can use that information to then obtain to obtain a good policy faster. So that's what we observe with this comparison of the results.
Gotcha. Yes, that's a really good clarification. So for the okay, there's like a question around the video of beam riders. So there, you mentioned that they had captured some horizontal lines, which are really part of the landscape. And I guess like the question is kind of like it captures some irrelevant information, but it's meant to capture motion in general, right? So if there's like any unrelated motion, then it will still be captured. Is that the case here?
Yes, that's exactly it. So here, yeah, those lines are irrelevant. It captures them because that's what the motion network does, right? So the segmentation network captures moving objects. And now the problem too is that you see those lines, they're bigger, they're just more important visually than you see the enemy. So like the enemy is like this little guy here, right? And then also you have some bullets that are being shot by both our agent and then the enemy, right? So then these things are small in comparison to the lines, so they don't get captured most of the time too. So now I guess there's a problem that it might capture visual effects that are irrelevant, and it might, as a result, not capture the things that are relevant. But then in our architecture, you see, let me go back. We still have a regular deep neural network that feeds into an actor critique where there's some convolution. So it also just uses the usual way of processing images. So if we feed in irrelevant information or information that does not contain the right stuff, then it can still be captured here, and that allows the policy to still be reasonable. Okay, but the top part now is computing information about those lines, which is really irrelevant.
Gotcha. Yeah, it definitely seems like even if there's some irrelevant information, it's overall not very harmful because of the architecture. So yeah, it definitely seems like that, and the results seem to show that as well. So another question is on, so there's like different games that you have, and I guess like were for each game you kind of just trained it from scratch, I guess. And I was wondering if the okay, so the part with the motion, the optical flow, like were you able to reuse it between games? Because I guess in all games they all have some sort of motion, right? Or was that different, separate for each?
Okay, yeah, that's a good point. So here we did not reuse it from one game to another, and that would be something natural to do. We did not do this for several reasons. So first of all, you see, we only use 1% of the frame. So when you look at the x-axis, right, 100,000 frames is like just this little part here. So that's the part where we were executing actions at random and just learning to segment. Now, the other baselines, like just regular A2C, which is in blue, is trying to optimize its actions from the start, but as you can see, it doesn't do any better, okay? Even at the beginning of the first 100,000 frames, it's executing actions at random anyway. I mean, not explicitly at random, but effectively at random, because it has no clue what it's doing anyway. So here, really, it doesn't matter. Like that 1% of the frame is tiny in comparison to the rest. So that's the first observation. The second observation is that the network tends to learn to be tailored to recognize objects that are special for each game. So like in Breakout, we have some objects that are different from Sequest, right? So here, well, the network is able to learn to recognize the objects that are relevant to Breakout or that are moving in Breakout specifically, and then it does well after that. But if we transfer that to Sequest, then it would require a lot more optimization to have something that can just recognize moving objects in general. So here what we achieved in 100,000 frames would not work for Sequest after that. And the reality is that even within Breakout, like what we learned to recognize in the first 100,000 frames, that was based on executing actions at random, and very often the agent hasn't really gone far in the game by executing actions at random. So some games have multiple levels with different types of objects, different types of actions that need to be executed, and then here we continue to train the object segmentation part of the network throughout, okay, because then as the agent starts to explore different parts of the environment, there's going to be new objects, perhaps new level, and it needs to do a good job at recognizing those. So the idea is that it's continuously learning and continuously adapting based on this. And what we've observed is that if we don't do that, then the results are not as good. So in fact, you can see here, joint means that it learns jointly both the top and the bottom part of the network. So the segmentation part of the network keeps on learning. Transfer means that we learn for 100,000 frames, then we transfer the weights, and then we don't continue learning after that. Okay, so this would be the purple line, and you see it doesn't perform as well as when we do joint learning. So there is value in continuing to learn, And also to do it across games, then we would have to continue learning as well for that. It might have a head start, but I don't think it's going to make much of a difference. At least the first 100,000 frames, you see, for all those baselines, nothing good happens really.
Gotcha. Gotcha. Okay, quick clarification, and I think maybe I just like missed it. Is like, so for the transfer, it's kind of like you freeze the, I guess like the top part, the part with the optical flow, but then you freeze that part, and then you just kind of like feed it in. But then the joint is like you both are continuously learning. And I'm just wondering, like at the time that for the transfer, like by the time you froze it, like is it like the same amount of, let's say, like iterations or like training, or like is it like learning for less time than the one in joint, or is it the same?
Well, okay, yeah, so in transfer, it's learning for 100,000 iterations and that's it. After that, it's frozen. For joint, it just learns all the way through. So all 10 million frames.
Gotcha. Thanks. I just suddenly forgot for a second. Yeah. Awesome.
Yeah.
So that's really helpful. That's very that's actually a really interesting comparison. I guess. Okay, just one last question then, because I know
Mhm.
there's been quite a few. Just I guess out of curiosity, because you had a slide where you mentioned, yeah, it's like actor critic, but then you also have PPO, and I'm wondering, what were the main, I guess, like as to your guess as why to their performance was different? Is it because, like, I guess, does it seem like the critic part is really helping, or um yeah, I guess I'll let you kind of talk about that.
Um, well, so here you see our technique, which is to have this segmentation network combined with some actor critique technique. Um, like our segmentation network can be combined, in fact, with any RL technique, because the RL technique, whether it's A2C PPO, is not changed. Um, and then so then we simply, yeah, feed or concatenate, you see, information that comes from the segmentation network. So here, I guess, why is it that we don't get results that are as good for PPO as A2C? I guess maybe the natural thing to say is just that PPO anyway has been shown to be better than A2C, right? So there might not be as much in terms of improvement that can be achieved with PPO. But then, is there something about the critique specifically that gets affected? I'm not sure, because you see, the information we get from the segmentation network is useful for both the critique and the actor, right? So I don't think there's anything specific about the critique per se here that affects anything. So it's really just that with PPO, it's a better algorithm than E2C. It's known to converge faster, so therefore there's less room for improvement, and that's exactly what we observed here.
That okay, that makes sense. Yeah, I was just like curious what you observed or thought about that. So I guess that's all of the questions for now. And yeah, thank you very much for the talk. Like it was very, like I really enjoyed it personally, and I'm sure the audience did as well. So once again, thanks everyone for tuning in, and we'll have many more talks like this in the future. Thank you.
Okay, thank you as well.
Okay, we will be going offline.